how did the dinosaurs really die? You already know the asteroid killed the dinosaurs. Everyone knows that. It's on lunchboxes and museum gift shops and documentaries that play on Sunday afternoons. Giant space rock, massive explosion, dinosaurs gone. Story over. But here's what they don't tell you on those lunchboxes, and what most documentaries gloss over in their rush to get to the dramatic CGI explosion. The asteroid wasn't a delete button. It was the first domino in a chain of disasters that stretched across time and space in ways that are genuinely difficult to comprehend. What actually killed the dinosaurs was a cascading nightmare of catastrophes that played out across days, weeks, months, years, and possibly even decades. Different animals died in different ways, in different places, on completely different timelines. Some died instantly, vaporized before they could process what was happening. Some died slowly, over weeks of starvation and environmental collapse. Some almost made it, surviving the initial chaos only to succumb to the long fade of ecosystem breakdown. And today, we're going through all of it. 10 ways dinosaurs died. This is not a countdown. We're not building suspense by saving the real answer for last. We're starting with number 1 because the asteroid absolutely deserves top billing. It earned that spot. And then we're going to keep going. Because the real story, the story that actually explains why the extinction was so thorough and so devastating, is what happens after the impact. The impact was the trigger. Everything else was the execution. When I say dinosaurs died, I mostly mean non-avian dinosaurs. The big, famous ones. The ones you think of when someone says the word dinosaur. Because spoiler alert, and this is not a secret in paleontology, some dinosaurs didn't die. We'll get to that in the finale, but we need to go back. We need to rewind the clock 66 million years. We need to visit a world that is about to change forever. Number 1, the impact itself. Picture this and really try to put yourself in this moment. You're a dinosaur on the coastline of what will someday, millions of years in the future, be called Mexico. You have no concept of space as a place where things exist. You don't know what an asteroid is. You don't know what orbital mechanics means. You don't even know that objects can fall from the sky with hostile, universe-ending intent. Your entire world, your entire experience of reality is find food, avoid predators, defend your territory, raise your young, find shade when the sun gets too hot, find warmth when the night gets too cold. Normal dinosaur stuff, evolutionary success stories. You're part of a lineage that has dominated Earth for over 160 million years. Then the sky develops a problem, and it's a problem that escalates faster than any nervous system can process. The Chicxulub impactor was roughly 10 to 15 kilometers across. To give you a sense of scale, that's about the size of Mount Everest, traveling at cosmic speeds, multiple kilometers per second, and it slammed into the Yucatan Peninsula with the force of billions of nuclear weapons detonating simultaneously, excavating a crater roughly 180 kilometers wide. Let me repeat that, 180 kilometers wide. That's not just a hole in the ground. That's not a crater. That's a geographic restructuring event. That's the planet's crust being punched so hard that it rebounds, that it melts, that it behaves like a liquid for a few terrible moments. And if you're near ground zero, if you happen to be one of the unlucky dinosaurs within a few hundred kilometers of the impact site, you don't get a story arc. You don't get a dramatic final moment where you look up at the sky and understand what's happening. You don't get time to run, or hide, or protect your young. You experience physics at its most brutal and unforgiving. Rock turns to vapor. Temperatures exceed those on the surface of the sun. The ground becomes plasma. The air becomes shockwave. Matter doesn't just break, it changes state entirely. No chase scene, no last glance at the horizon, no poignant moment of realization. Just matter changes state, and you are matter. Now, and this is important to understand, most dinosaurs weren't standing at ground zero. The impact site, while catastrophically large, represents a tiny fraction of Earth's surface. Most dinosaurs, the vast majority of them, died in ways that look less like a single explosion and more like a cascade of connected disasters, each one feeding into the next, each one making the situation worse. For now, for this #1 slot, the headline is The Big Space Rock. It's the opening act, the catalyst, the thing that starts the dominoes falling. But the opening band, the supporting disasters, the cascade of consequences, that's where things get truly, systematically horrifying. Number 2, a dinosaur can be killed by the sky. Not because a predator swoops down from above, not because a pterosaur is having a particularly aggressive day and decides to attack something it normally wouldn't. Not because of any natural predator-prey dynamic, because the atmosphere itself becomes a radiant grill, a planetary-scale heat source. Here's what happens, and the mechanism is both elegant and horrifying. The impact throws enormous quantities of material up into space and high into the upper atmosphere. We're talking about millions of tons of rock, pulverized and superheated. Some of this material achieves escape velocity and leaves Earth entirely. Some of it goes up and then comes back down. And when it comes back down, when it re-enters the atmosphere at high velocity, friction heats it. The sky, all around the planet, becomes filled with glowing, superheated particles. Even thousands of kilometers from the crater, even on the opposite side of the planet. This isn't a pretty meteor shower that you watch and admire. This isn't a few shooting stars. This is a planetary-scale heat event, a thermal pulse that radiates downward from the sky itself. So imagine you're a large herbivore in a forested region, far from the impact site. Maybe you're in what will one day be Montana. Maybe you're in what will one day be Mongolia. Distance doesn't protect you from this particular disaster. You're not vaporized, you're not at ground zero. You're not crushed by falling rock or buried by ejecta. You're not drowned by a tsunami. Instead, the world just heats up, quickly enough, intensely enough, to do serious biological damage. Your eyes start to burn, your skin blisters, your lungs struggle to process superheated air. If you have feathers or proto-feathers, they might ignite. Panic spreads through your herd, through your family group. All around you, trees and undergrowth begin to smoke, then smolder, then ignite. The forest you've lived in your entire life, that your species has lived in for millions of years, starts burning. And here's what makes this mechanism especially cruel, especially psychologically devastating if dinosaurs had the capacity to understand what was happening to them. It arrives as light. There's no roar of an approaching predator. There's no warning smell of smoke before the heat arrives. There's no natural disaster you can read and respond to based on evolutionary experience. There's no predator you can run from, no rival you can fight, no storm you can shelter from. Just brightening, the sky getting brighter, then brighter still, then the heat hits you, and then pain. But wait, because there's a second part to this horror, a secondary disaster that makes this mechanism not just locally devastating, but globally significant. Once vegetation ignites, once forests start burning on a massive scale, you get secondary disasters that compound the original problem. Wildfires aren't just a local problem, they're not just some trees burned here. They become a climate problem. They become an atmospheric problem. They release enormous quantities of soot, carbon particles that rise into the upper atmosphere. And soot matters. Soot is important because it absorbs sunlight. It changes the energy balance of the entire planet. Scientists have modeled, using sophisticated climate simulations, how soot and impact-generated aerosols could have reduced sunlight reaching Earth's surface and cooled the planet, undermining photosynthesis across the entire globe. This is the lead-in to impact winter, which we'll get to in detail later. So in this number 2 slot, dinosaurs die in 2 connected ways, 2 mechanisms that feed into each other. Direct heat injury and fire exposure in the immediate aftermath of the impact. Ignition of vegetation on a continental or global scale that feeds into later disasters, specifically the darkness and cooling that will starve the survivors. This is the first moment where you can really feel the extinction shift from spectacular disaster to systematic failure. Number 3. The air becomes a weapon. There's a special kind of horror in stories where the atmosphere, the thing you breathe and move through without thinking about it, the invisible background of existence, stops being background and becomes the antagonist. The impact produced an immense pressure disturbance. Call it shock waves, call it blast winds, call it an atmospheric pressure wave. Whatever terminology you prefer, the physics is the same. Air moving at extreme velocity, carrying enormous kinetic energy. Near the impact, within a few hundred kilometers, this is catastrophic beyond description. The atmosphere itself becomes a wall of force moving at supersonic speeds. Farther away, at distances of thousands of kilometers, it's still powerful enough to flatten forests, tear apart habitats, collapse structures and injure animals directly. Now, imagine you're a mid-sized predator, not a giant like Tyrannosaurus, but something more gracile, something that relies on speed and agility. Maybe you're a dromaeosaur, one of the raptor family. You're built for precision. You rely on speed, on balance, on razor-sharp sensory focus. You're a successful hunter. You understand your territory intimately. You know where prey congregates, where water sources are, where good ambush points exist. You're confident. You're at the top of your local food web. And then the air arrives like a wall. This isn't wind you lean into, adjusting your posture and waiting for it to pass. This isn't a storm you can read and prepare for based on changes in air pressure or cloud formation. This isn't weather in any sense that evolution has prepared you for. It's a moving front of force that can knock you over, that can fling debris like artillery shells, that can strip away the cover you depend on for hunting, that can shred the vegetation that conceals your approach to prey. Animals die here from blunt trauma, from being struck by flying debris. They die from being thrown into obstacles, from tumbling end over end until bones break. They die from being caught in collapsing vegetation, pinned under fallen trees. They die from being buried under landslides triggered by the pressure wave. But there's another twist, another mechanism that makes this even more devastating. Blast winds don't just push air, they turn landscapes into projectiles. Branches become spears, stones become bullets. Even clods of earth, chunks of soil ripped from the ground become weapons. The environment itself attacks you. Everything that was stable and solid and safe becomes mobile and dangerous. So for number 3, you can say this with complete accuracy. Dinosaurs died because the atmosphere briefly behaved like a fast-moving solid, like a horizontal avalanche made of air. Number 4. Dinosaurs die because the ocean decides to do architecture. The Chicxulub impact produced tsunamis, and there's peer-reviewed modeling published in reputable scientific journals of a global tsunami from the impact. Not just local waves near the Gulf of Mexico. Global. Waves propagating across ocean basins, refracting around continents, arriving on distant shores hours after the impact. These weren't normal waves. These weren't even hurricane storm surge. These were oceanic walls of water, hundreds of meters high in some locations, laden with debris, moving with unstoppable momentum, carrying the kinetic energy of a planetary-scale catastrophe. Now, and this is important for understanding why the death toll varied so much by location, it matters that coastlines aren't uniform. Some coasts are protected by geography, by offshore islands that break up wave energy, by deep offshore trenches that dissipate momentum. Some coastlines funnel waves through narrowing bays, amplifying them through a process called resonance. Some have shallow continental shelves that concentrate the energy, making the waves grow taller as they approach shore. So the same event, the same impact, creates different death stories across different coastlines. Some regions experience rapid inundation. Some experience devastating but survivable flooding. Some experience waves so large they reshape the entire coastal geography. Let's build a coastal scene. Let's make this concrete and specific. A herd of hadrosaurs is moving along the shore. They're large herbivores, duck-billed dinosaurs, and they're feeding on low coastal vegetation. Salt-tolerant plants. Maybe they're migrating, following seasonal food sources. Maybe they're just living their lives, doing what hadrosaurs do, which is eat enormous quantities of plant matter and occasionally make loud honking noises to communicate. It doesn't matter what their specific activity is, because the hazard isn't a predator stalking them. It isn't a rival herd competing for territory. It isn't a drought or a food shortage. It's the shoreline itself changing shape. First, and this is a classic pre-tsunami signal that appears in historical records of human tsunami experiences, the sea might pull back. Water retreats, exposing unfamiliar ground. Stranded fish flop on exposed seafloor. Coral reefs that are normally underwater suddenly appear. The beach extends outward, revealing shells and stones and marine life struggling in pools of water. That's the ocean pulling back, drawing water away from shore to feed the approaching wave. But no dinosaur has tsunami folklore. There's no cultural knowledge passed down through generations. There's no elder hadrosaur standing on the beach, watching the water retreat, turning to the younger members of the herd and saying, "When the sea runs away, you run too. You run inland as fast as you can, and you don't stop running." They don't know what's coming. Then the water returns. Not as a wave you can surf, not as something you can swim through or dive under, as a moving wall, a cliff of water heavy with debris, fast as a freight train, loud as continuous thunder. Animals die by drowning, by being unable to breathe as water closes over them. They die by impact with debris, struck by logs or rocks or even other struggling animals. They die by being smashed into obstacles, crushed against cliffs or trees. They die by being dragged into turbulent backwash, the water rushing back toward the ocean, carrying them out to sea and breaking them apart in the churning chaos. Now, picture the wave after the first wave. Picture the landscape after the water recedes. Because even if you survive the initial inundation, even if you're lucky enough to be in a high spot or far enough inland or just incredibly fortunate in your positioning, the landscape is shredded. Nests destroyed, eggs smashed, burrows flooded and collapsed, food sources obliterated, buried under meters of marine sediment. Fresh water sources contaminated with salt, the entire coastal ecosystem reshaped, familiar territories rendered unrecognizable. And that matters more than the immediate death toll, because survival after a catastrophe depends on intact habitat. In extinction events, and this is a pattern that shows up repeatedly in Earth's history, the second killer is often not the dramatic moment. It's not the spectacular disaster. It's the loss of the ordinary, the loss of the familiar places where you eat, where you rest, where you mate, where you raise your young. The loss of the ecological infrastructure that allows life to continue. The tsunami kills immediately, but it also kills slowly by removing the possibility of recovery. Number 5. The planet rings like a struck bell. Large impacts transfer energy into the crust. This is basic physics, basic energy transfer. Call it seismic waves, call it regional earthquakes, call it slope failure, call it widespread ground disturbance, call it the Earth behaving like a giant drum that's just been hit harder than it's been hit in millions of years. Whatever terminology you use, the outcome is the same for animals living under cliffs, living near unstable slopes, living in forests on soft ground, living in regions with geological instability. The ground stops behaving like ground. The fundamental assumption of existence, that down is stable and solid and reliable, suddenly becomes false. Imagine it's nesting season in a rocky upland region. Maybe you're a smaller theropod, something like Troodon, and you've chosen this location specifically because it offers protection. The rocky terrain makes it harder for larger predators to approach unseen. The elevation gives you a good view of approaching threats. The rocks hold heat, keeping your eggs warm. Eggs are laid in shallow nests carefully arranged, some buried in soil for temperature regulation, some exposed to sunlight. Adults are nearby, constantly vigilant because, in normal circumstances, the threats to eggs are numerous: theft by small mammals, trampling by larger dinosaurs, opportunistic predators, temperature fluctuations. In normal years, those are the challenges, those are the problems evolution has equipped you to handle. Then the ground shakes. A tremor isn't just a tremor, isn't just a brief, unsettling sensation. It triggers rockfall, sending boulders tumbling down slopes. It snaps branches that were already stressed. It collapses cliff edges that were already weathered and weakened. It destabilizes slopes, starting landslides that fill valleys with debris. It crushes nests under falling rocks. It buries animals alive. It transforms stable landscapes into chaotic, mobile danger zones. Even animals that can run, that are built for speed and agility, cannot outrun a hillside. You cannot outrun gravity when the entire slope decides to relocate itself to the valley floor. This is also where, and I want to note this because it becomes important when we talk about survivors later, small-bodied animals with burrowing behavior can sometimes have a significant advantage. Not because burrows are magical, not because being underground automatically protects you from everything, but because a properly constructed burrow provides a stable microenvironment during short intervals of surface chaos. If you're in a burrow during an earthquake, you might be safer than you would be on the surface, where rocks are falling and trees are toppling. We're not at the survivors section yet. That comes in the finale, but notice the pattern that's forming. The traits that help you survive catastrophic events aren't heroic traits. They're not the traits we celebrate or put in movies. They're not strength or size or being the apex predator. They're boring traits: smallness, flexibility, the ability to hide effectively, not needing much food, being able to eat a wide variety of things, living in a hole in the ground, being comfortable in marginal environments that more specialized species avoid. Number 6. Dinosaurs die because the sky becomes chemistry. When Chicxulub hit, when it vaporized rock and lofted material into the atmosphere, it didn't just throw up inert dust. It vaporized and lofted material that included sulfur-bearing rocks, rocks rich in compounds that, when mixed with atmospheric water, form sulfuric acid. Sulfur aerosols and atmospheric reactions can produce acid rain. There's also scientific discussion of nitric acid rain formation via nitrogen oxides, produced during the intense heating of the impact when atmospheric nitrogen and oxygen are forced to react under extreme temperatures. Now, and this is important to understand because it shapes how this disaster unfolds, acid rain isn't a single cinematic explosion. It's not a moment. It's not something you can point to and say, "There. That's when the acid rain killed them." It's the slow horror of irritation, poisoning, and ecosystem damage spread across weeks and months. If you're an animal drinking from shallow water sources like ponds or streams, you're consuming increasingly acidified water. If you're browsing leaves covered in acidic residue, you're getting chronic low-level chemical exposure. If you're relying on a sensitive respiratory system, like many dinosaurs with sophisticated air sac systems, you're breathing in aerosols that damage lung tissue. You're constantly exposed to what we can politely call an environmental irritant package. So how do dinosaurs die here? What's the specific mechanism? It's not usually sudden, it's not a dramatic collapse, it's a grinding pressure that wears down survival capacity. First, damaged vegetation reduces food quality and availability. Plants stressed by acid deposition don't grow as well. They don't produce as much foliage. What they do produce might be less nutritious, or harder to digest, or covered in chemical residue that causes gastrointestinal problems. Second, eye and lung irritation increases vulnerability to predation and exhaustion. If your eyes are constantly watering, your vision is impaired. If your lungs are damaged, you can't run as far or as fast. You become easier prey. You're less effective at escaping threats. Third, contaminated water stresses physiology. Your kidneys work harder to filter out toxins. Your liver is under constant load. Your immune system is compromised by chronic chemical exposure. Fourth, and most importantly for the long-term extinction dynamic, ecosystems begin to unravel, particularly in already stressed regions. Acid-sensitive species die first, creating gaps in food webs. Those gaps cascade upward through predators and downward through decomposers. In the oceans, chemical shock matters even more. The KPG boundary, the geological layer marking this extinction event, is associated with massive disruptions in marine life. There's scientific discussion, ongoing research and debate about ocean acidification after the impact. The exact degree to which acidification drove particular marine extinctions is still being worked out. The science is nuanced and complex, but the basic mechanism is clear. Dump enough acid-forming compounds into the atmosphere, and eventually ocean chemistry changes. Ocean acidification particularly affects organisms that build shells or skeletons from calcium carbonate. The chemistry becomes hostile to shell formation. Tiny marine organisms, plankton that form the base of the oceanic food web, start dying, and when the base of the food web collapses, everything above it eventually follows. Even if you're a dinosaur that survived the heat, survived the blast wind, survived the tsunami, survived the earthquakes, you still have to drink. And when the water turns hostile, when every drink comes with a dose of chemical stress, survival becomes a daily negotiation with invisible forces you cannot fight, cannot flee from, and cannot possibly understand. Number 7. The world catches fire, and then the fire changes the sky forever. We already met fire as a local consequence of the thermal pulse back in number 2. Now we need to treat fire as what it actually becomes, a planetary-scale ecosystem disruptor, a transformation of the very composition of the atmosphere, Because large fires burning across continents, aren't just heat and flames destroying things locally. They're habitat removal on a massive scale. They're air quality collapse. They're the conversion of forests and grasslands and everything green and living into ash and soot and carbon. And soot matters. Soot is critically important to understanding why this extinction was so thorough. Because soot doesn't just disappear. It doesn't just settle out of the air immediately. It goes up, carried by the heat of the fires themselves, rising into the upper atmosphere, where it can stay suspended for months or even years. And while it's up there, it absorbs sunlight. It changes the energy balance of the entire planet. It alters temperatures. It reduces the light reaching the surface. This ties directly, this is the bridge, into the impact winter story we'll get to in the next section. So let's build a different kind of scene here, one focused on behavior rather than immediate physical trauma. A large sauropod and a juvenile, let's say they're titanosaurs, huge long-necked herbivores, among the last of their kind at the end of the Cretaceous. They're not killed instantly by the fires. The flames don't catch them directly. They're displaced. They become refugees in their own world. They roam, trying to find familiar feeding routes, but they cannot because the landscape has transformed into a mosaic of burn scars and active fire fronts and smoke columns rising like dark pillars. They breathe in particulates constantly. Every breath carries ash. Their eyes water, their vision blurs. Their mucous membranes in their noses and throats become inflamed and damaged. Their movement becomes inefficient because they're spending more energy trying to find food while taking in less oxygen per breath. Predators, also desperate, also displaced, also struggling, take risks they wouldn't normally take. A healthy adult sauropod is too large to attack, but a stressed one, a weakened one that's been breathing smoke for days and can't move quickly, that becomes tempting. The normal rules of territory break down. The social structures that kept predator and prey populations in balance collapse. The world becomes both emptier and more dangerous. Emptier because so many animals have died. More dangerous because the survivors are desperate. In fire ecology, the science of how fires affect ecosystems, there's a grim principle that ecologists learn early in their training. After a massive burn, it's not just the flames that kill, it's what the burn takes away. Cover that animals use to hide from predators or shade themselves from sun. Food sources, the plants they evolved to eat. Clean water, now contaminated with ash and debris. Familiar shelter, the specific trees or rocks or burrows they return to. Nesting sites, locations chosen through generations of trial and error. Migration corridors, the routes they traveled seasonally. All of it gone, all of it transformed into a monochrome landscape of ash. And that's extinction logic right there. That's the mechanism that turns a disaster into a mass extinction. A species can survive individuals dying. That's normal. That happens constantly. Predation, disease, accidents, old age, individual death is part of life. What a species cannot survive is the removal of the conditions that allow life to continue. The removal of habitat, the removal of food sources, the removal of the ecological infrastructure that made their particular survival strategy viable. Number 8. Dinosaurs die because the planet goes dark. This is the slow killer that follows all the spectacular ones. This is the disaster that unfolds over months and years rather than seconds and minutes. Aerosols block sunlight. Dust blocks sunlight. Soot, as we just discussed, blocks sunlight and absorbs it. Less sunlight reaching Earth's surface means reduced photosynthesis. Reduced photosynthesis means plants fail to grow, fail to produce energy, begin to die back. When plants fail, herbivores starve because their entire survival strategy is built around the availability of plant matter. When herbivores starve and their populations crash, carnivores either starve later as their prey base vanishes, or they fight harder over the remaining prey, accelerating the collapse. There's extensive scientific modeling on the impact winter concept. Climate scientists have run simulations, sophisticated computer models, analyzing the role of soot and aerosols in reducing light and cooling the surface. The details are complex, the exact magnitude and duration are still debated, but the basic mechanism is well established. This is where dinosaurs face what might be the most insulting enemy of all, not a rival species competing for resources, not a predator hunting them, not fire or flood or earthquake or any dramatic natural disaster, not the sky, not the ocean, not the air, just no food. Just the slow realization, if dinosaurs could realize such things, that there is nothing left to eat and nothing is growing to replace what's already been consumed. Let's focus on a large plant eater because the mechanics are clearest here. Pick a specific example. Let's say an Alamosaurus, a massive sauropod from what is now Texas and New Mexico. Big body which requires enormous daily caloric intake. Slow reproduction, which means population recovery takes generations. High daily food requirements, maybe hundreds of kilograms of plant matter per day just to maintain body temperature and basic metabolism. Narrow dietary preferences evolved over millions of years to efficiently process specific types of plants. Under normal conditions, this animal is an evolutionary success story. It's perfectly adapted to its environment. It has exactly the right tools, the right digestive system, the right behavior, the right everything for a world full of plants. In impact winter conditions, every one of those successful adaptations becomes a liability. You cannot browse what isn't growing. Your specialized digestive system, so efficient at processing large quantities of specific plants, becomes useless when those plants are dead or dying. Your enormous body, which gave you advantages in normal times like the ability to reach high vegetation and the ability to defend against predators, now requires more food than the devastated landscape can provide. You can walk farther, searching for green vegetation, searching for anything edible. But the landscape is damaged and unfamiliar. The markers you used for navigation, the specific trees or rock formations you remembered, might be gone or obscured. Migration is harder because the routes are damaged. Energy costs rise because you're walking more and finding less. Predation risk increases because you're traveling through unfamiliar territory and you're weakened. Reproduction falters because females don't have enough resources to produce eggs, and even if they do, there's no food for juveniles. Eggs laid into a world with a collapsing food supply don't represent hope for the future. They represent a delayed tragedy, more mouths that cannot be fed. Now consider a carnivore. Let's say a tyrannosaur because everyone knows Tyrannosaurus rex and the mechanics are illustrative. At first, immediately after the impact and during the initial die-off, there's carrion everywhere. Dead animals, dying animals, weakened prey that's easier to catch than it would normally be. So carnivores might briefly do well in the absolute worst, most temporary sense of that word. There's food available. More food than usual in some places. A tyrannosaur could eat without hunting, just scavenging from the casualties of the disasters we've already discussed. But then the carrion is gone, it's been consumed or it's rotted, and the prey base, the living animals that would normally sustain a predator population, has collapsed. The herbivores are starving, which means they're dying, which means there are fewer of them. The system is emptying out, and carnivores crash too. But they crash with a lag. weeks or months after the herbivores, because they can survive a little longer on the remaining prey. Extinction is not always a single moment. Sometimes it's a staggered silence, populations winking out one after another in sequence. And yes, this is where dinosaurs discover the downside, the fundamental cosmic unfairness of being large, charismatic megafauna. Turns out the universe doesn't care that you're iconic. The physics of starvation don't care that you're the most successful predator who ever lived or the largest land animal of your era. Metabolism is metabolism. Energy is energy. No food means death, no matter how impressive you are. Number 9. Dinosaurs die because the planet was already stressed and then it got worse. The Deccan Traps in India represent one of the largest volcanic events in Earth's history, a period of massive flood basalt volcanism around the end of the Cretaceous period. And there's active, ongoing scientific debate, with new papers being published regularly about how much Deccan volcanism contributed to the KPG extinction alongside the Chicxulub impact. This isn't fringe science. This isn't speculation. This is serious researchers looking at serious evidence and asking, was the asteroid the only killer, or was it the final blow to an already dying world? Here's what we know, and here's why this matters. Even before the asteroid hit, some ecosystems may have been dealing with significant climate volatility and environmental stress. Volcanism on the scale of the Deccan Traps doesn't just create lava flows, it releases enormous quantities of carbon dioxide, which causes warming. It releases sulfur aerosols, which cause cooling episodes and acid rain. It releases toxins like mercury, which accumulate in food webs and cause all sorts of physiological problems. It creates climate instability, swings between warming and cooling, making it difficult for species to adapt. Some evidence suggests that certain groups of organisms were already declining before the impact. The fossil record, when examined closely, shows patterns that might indicate stress in the final million years of the Cretaceous. Not a collapse, not yet, but pressure. Ecosystems operating closer to their breaking points. Then the asteroid arrives and delivers a catastrophic shock to systems that were already struggling. In other words, the asteroid is the headline, the thing everyone remembers, the dramatic moment that makes it into documentaries and textbooks. But volcanism may have been the background pressure, the chronic stress that left ecosystems vulnerable. So how does volcanism kill dinosaurs? What are the specific mechanisms? First, longer-term climate change that shifts habitats faster than species can adapt. If you're a species specialized for a particular temperature range, a particular rainfall pattern, a particular type of vegetation, and those conditions start changing over thousands of years, you have to either adapt, migrate, or die. And adaptation is slow. Evolution works across many generations. If the environment is changing faster than evolution can respond, populations decline. Second, acid rain and ocean chemistry changes affecting food webs from the bottom up. Volcanic sulfur aerosols create sulfuric acid. It falls as rain. It enters rivers and eventually oceans. It stresses marine organisms, particularly those that build shells or have calcium-based structures. Marine food webs begin to fray, starting with the smallest organisms and cascading upward. Third, mercury and other toxic emissions acting as physiological stressors. Mercury accumulates in tissues. It's neurotoxic. It affects reproduction. Animals at the top of food chains, predators eating contaminated prey, accumulate the highest concentrations. This is biomagnification, the same process that affects modern ecosystems contaminated with heavy metals. Fourth, ecological fragmentation across time. Species ranges shift, Populations become isolated from each other. Genetic diversity decreases, local extinctions accumulate. The overall resilience of ecosystems, their ability to absorb shocks and recover, declines. If Chicxulub is a sledgehammer to the head, a single devastating blow, Deccan is a sustained shove, a continuous pressure pushing ecosystems toward collapse. You can survive a shove. You can recover from a shove. Species are resilient. Life is resilient, given enough time at stable conditions. But if the asteroid is about to remove stability everywhere, if it's about to hit every ecosystem simultaneously with multiple cascading disasters, then the shove becomes decisive. The prior stress becomes the difference between survival and extinction. The KPG extinction probably wasn't just an asteroid killed the dinosaurs. It was probably volcanic stress weakened ecosystems. Then an asteroid delivered multiple simultaneous catastrophes to already vulnerable systems, creating a cascade of failures that nothing could survive. That's less catchy. It doesn't fit on a lunchbox as easily. But it's probably closer to what actually happened. Number 10. Dinosaurs die because, after surviving all the disasters, the survivors are trapped in a numbers game they cannot win. This is the least cinematic ending of all 10, and it might be the most final, the most inevitable, the most quietly devastating. Because here's the thing, and this is important to understand about how extinctions actually conclude. After an extinction-level event, after all the spectacular disasters have finished playing out, you can have living dinosaurs still walking around, still breathing, still eating, still trying to reproduce while their species is effectively already finished. The outcome is already determined, even if the individual animals don't know it yet. Survival, the continued existence of a species, isn't just about one animal living through difficult circumstances. It's not just about individuals making it through the disasters we've discussed. A species, to actually persist across time, to have a future, needs, first, enough individuals to avoid catastrophic inbreeding. Small populations lose genetic diversity. Harmful recessive genes become expressed more frequently. Birth defects increase, fertility decreases. This is called an extinction vortex, where small population size creates problems that make the population even smaller. Second, enough habitat to sustain reproduction and allow juveniles to reach maturity. You need space for territories, for nesting sites, for finding mates. You need enough area that local disasters don't wipe out the entire remaining population. Third, enough stable food supply for juveniles to reach maturity and for adults to successfully reproduce. Reproduction is energetically expensive. Egg production, care of young, defending territories. If food is scarce, reproduction fails first. Fourth, enough time without new shocks to allow population recovery. Species can bounce back from low numbers, given time and stability. But if disasters keep hitting before populations can recover, the trend is always downward. Drop below a critical threshold in any of these requirements and recovery becomes implausible. Not impossible in the abstract, but so unlikely given real-world conditions that it functionally means extinction. Now I'm going to describe this in a way that's scientifically accurate and also emotionally devastating, because it captures something important about how the final phase of an extinction feels. You can survive the apocalypse and still lose to mathematics. You can be strong, you can be lucky, you can have good genes, you can do everything right on an individual level, and still be part of a population that's doomed because there simply aren't enough of you left. Imagine a small pocket of dinosaurs that made it through the initial weeks or months after the impact. Maybe they survived in a sheltered microclimate, a valley that avoided the worst of the fires, near a water source that stayed relatively clean, in a region where some vegetation survived. They're exhausted from constant stress. They're malnourished because food quality and quantity are both reduced. Their young are fewer because reproduction rates have dropped. Every successful hatching is now a rare event instead of a common one. They meet other survivors less often because the landscape has been fragmented, broken up by disasters into isolated patches. The continuous forests they once roamed have become islands of habitat separated by burned zones, by zones of chemical contamination, by zones that are simply dead. Migration corridors, the routes they travelled seasonally following food sources, are disrupted or destroyed entirely. The map they evolved to read, the landscape knowledge passed down through generations, no longer matches the actual world. They're also more vulnerable to disease and parasites than they would normally be because chronic stress weakens immune systems. This is well documented in modern animals. Stress hormones like cortisol suppress immune function, and crowded refuges, places where survivors concentrate because they're the only habitable areas left, can spread pathogens efficiently. Now, I don't want to lean too heavily on disease as a primary driver of the final extinctions, because the evidence for specific disease outbreaks in the fossil record is limited. But the broader point holds. The principle is sound. Once populations are tiny, once you're down to scattered remnant groups, 1,000 ordinary problems become lethal. Problems that would be minor challenges in a healthy population become population-ending events in a stressed, tiny population. A storm that destroys nesting sites. A cold snap that kills the weakest individuals and tips reproduction below replacement rate. A failed breeding season because not enough males and females find each other. A local drought that eliminates the last good water sources. A shift in predator pressure because the predators, also starving, focus on the remaining prey with desperate intensity. In a stable world, in normal times, these are challenges. They're obstacles that species navigate, that some individuals fail and some survive, that populations absorb and recover from. In a post-extinction world, in a world of fragmented populations and stressed ecosystems and depleted resources, they're finishers. They're the final blows that turn a struggling population into no population at all. And here's the weird emotional twist, the point where the narrative becomes uncomfortable. This is where the story stops being about dinosaurs specifically and starts being about what kind of life survives catastrophe. What traits predict survival when everything collapses? What strategies work when the normal rules stop applying? Because if you look at what actually survived the KPG extinction, if you examine the winners rather than focusing only on the losers, a pattern emerges. The animals that persist, that make it through and repopulate the world, aren't the kings and queens of the old world. They're not the biggest, not the strongest, not the most specialized, not the apex predators, not the most impressive megafauna. They're the scrappy generalists, the small opportunists, the ones that can eat many different things instead of specializing in one food source. The ones that reproduce quickly, multiple generations per year, instead of one offspring every few years. The ones that hide effectively in burrows or water or dense vegetation. The ones that live in marginal spaces nobody else wanted, the ecological leftovers. The survivors are, in many ways, the unremarkable species, the ones that would never get their own documentary series. The ones that don't inspire children's toys or museum exhibitions. If you want the real moral of the KPG extinction, if you want the lesson that applies across mass extinctions throughout Earth's history, it's not be strong. It's not be the apex predator. It's not dominate your ecosystem. It's be adaptable, be flexible, Be small, reproduce quickly, eat many things, and maybe, just maybe, enjoy burrows and water and not being picky about food. It's specialization is a trap when the world changes too fast. And there's something both humbling and terrifying about that realization. The dinosaurs weren't weak. They weren't failures. They dominated Earth for over 160 million years, which is an almost incomprehensible span of time. They evolved extraordinary diversity, extraordinary adaptations, extraordinary success. And it didn't matter. When the asteroid hit, when the cascading disasters began, all that evolutionary success became irrelevant. Being the most successful predator who ever lived didn't help Tyrannosaurus rex. Being the largest land animal didn't help the sauropods. Being perfectly adapted to your environment became a liability when that environment stopped existing. That's the final way dinosaurs died, slowly, in scattered groups, losing to mathematics and ecological reality, even after surviving the spectacular disasters. Not with a bang, but with a whimper. Not in dramatic last stands, but in quiet population declines. Not as heroes in their own story, but as victims of circumstances beyond their control or comprehension. Okay, deep breath. Time for the aside section, where we deal with the fact that the word dinosaurs has been doing some heavy lifting throughout this entire video, because the truth, the scientifically accurate truth, is more complicated and more interesting than all dinosaurs died. Some survived, some lineages continued. Some are still here, and we need to talk about that. Aside A. Dinosaurs evolved into birds, which means dinosaurs didn't entirely die. This isn't a quirky opinion or a fun theory that some scientists believe and others dispute. This isn't controversial. This is mainstream paleontology, supported by overwhelming fossil evidence and confirmed through multiple independent lines of research. Birds are living dinosaurs, direct descendants of theropod dinosaurs, specifically Maniraptoran theropods. When you look at a bird, you're not looking at something that's like a dinosaur or related to dinosaurs. You're looking at an actual dinosaur, a living, breathing, modern dinosaur that survived the KPG extinction because its ancestors had traits that happened to be useful during a planetary catastrophe. It is fascinating, isn't it, to think that those annoying pigeons that regularly leave messes on cars are descendants of Velociraptor. Perhaps that's a subject that can be brought up at your next dinner party. But let's be serious for a moment about why birds survived when their non-avian and pterosaur relatives didn't. Birds, or more specifically the bird ancestors alive during the KPG extinction, had several traits that proved crucial. Small body size, which meant lower food requirements. When food becomes scarce, being small is a massive advantage. You need fewer calories to survive each day. Flight capability in many lineages, which meant greater mobility. The ability to search larger areas for food. The ability to escape localized disasters. Dietary flexibility in many groups. Many early birds could eat seeds, insects, small animals, whatever was available. Generalist diets are survival gold during extinctions. Faster reproduction compared to large dinosaurs. Smaller animals generally reach sexual maturity faster and can have more offspring per year. Ability to exploit marginal habitats. Birds could nest in places that larger dinosaurs couldn't access, could feed in ecological niches that were too small or too unstable for megafauna. None of these traits were evolved for surviving asteroid impacts. Evolution doesn't work that way. Evolution doesn't plan ahead. These traits evolved for other reasons, in other contexts, over millions of years. They just happened to also be useful when the world ended. That's how evolution works. That's how survival works. random traits that happen to be useful when circumstances change. So when we say dinosaurs died, we need to be more specific. We should say non-avian dinosaurs died, and the avian dinosaurs survived and diversified and now represent over 10,000 living species distributed across every continent, including Antarctica. But that doesn't fit on a lunchbox as easily. Aside B, crocodilians and other reptiles. From that time still exist. Crocodilians are not dinosaurs. Let me be absolutely clear about that because the internet loves to get this wrong. Crocodilians, pterosaurs and dinosaurs shared a common ancestor back in the Triassic period, over 230 million years ago. They're archosaurs, members of the same larger group. But they diverged, they went down separate evolutionary paths, and crocodilians are their own distinct lineage. However, and this is what makes them interesting for our purposes, crocodilians are a very ancient lineage that survived the KPG extinction. Modern crocodilians are the descendants of animals that lived through the same catastrophes that killed the non-avian dinosaurs. So why did crocodilians survive when so many dinosaur lineages didn't? Their semi-aquatic lifestyles are often discussed as a major survival advantage. Water provides temperature stability. Water provides protection from fire, from heat pulses, from many of the atmospheric disasters we discussed. Aquatic animals could potentially ride out the worst of the immediate catastrophes submerged. Lower metabolic rates compared to many dinosaurs, especially compared to the warm-blooded or quasi-warm-blooded theropods and ornithischians. Lower metabolism means lower food requirements. When food becomes scarce, low metabolism is a tremendous advantage. Dietary flexibility. Many crocodilians are opportunistic predators and scavengers. They can eat whatever's available: fish, carrion, small animals, anything they can catch or find. That generalist strategy once again proves valuable during catastrophes, ability to fast for extended periods. Modern crocodilians can go months without eating. That ability probably existed in their ancestors. When food becomes unpredictable, the ability to survive long fasts is crucial. Tough, armored skin that provides some protection from environmental hazards and from the chemical stresses we discussed in earlier sections. Turns out, being comfortable in water and mud is a very good strategy when the land is on fire and the sky is trying to poison everything. Being able to hold your breath and submerge yourself is excellent when the atmosphere becomes temporarily hostile. Being cold-blooded, which is usually discussed as a disadvantage in biology classes, becomes an advantage when food disappears and you need to survive on minimal resources. There's a broader lesson here about survival strategies. The traits we typically celebrate, the ones that seem impressive and powerful: warm-bloodedness, high metabolism, specialization, large body size, are often liabilities during catastrophes. The traits we typically ignore, the ones that seem like limitations: cold-bloodedness, low metabolism, small size, generalist diets, are often the keys to survival. Evolution doesn't care about impressive. Evolution cares about still alive tomorrow. Aside C, oceans, kilometers beneath Earth's crust. Okay, this is where we need to be very careful, because this is where popular science headlines diverge significantly from what the actual science says. And I want to address this because it shows up in comment sections, it shows up in speculative discussions, and it's important to understand what's real and what's exaggeration. Science has presented evidence, published in reputable peer-reviewed journals, that the mantle transition zone, which is a layer deep inside Earth, roughly 400 to 660 kilometers below the surface, may hold vast quantities of water locked inside mineral structures. Specifically, the mineral ringwoodite can incorporate water into its crystal structure. Not liquid water, not water you could drink or swim in. Water molecules chemically bound into the mineral lattice under extreme pressure and temperature. When researchers calculate the total amount of water potentially stored this way across the entire mantle transition zone, the numbers are staggering. The estimates, sometimes described in headlines as an ocean's worth of water, or even multiple oceans' worth in terms of total hydrogen and oxygen content. But, and this is the critical point that headlines often miss or deliberately obscure for drama, that does not mean there are literal liquid oceans down there that you could access, that you could swim in, that you could build submarines to explore. This is not Jules Verne's Journey to the Center of the Earth. This is not a vast underground ocean with its own ecosystem and mysterious creatures. This is water held in mineral crystal structures under extreme pressure, over 100,000 times atmospheric pressure, and extreme temperature, over 1,000 degrees Celsius. It's chemically bound. It's not flowing around like an underground sea. You can't drill down and tap it. You can't send explorers to visit it. So, could dinosaurs be living kilometers beneath the crust in some hidden ocean realm? As science, as actual physical reality, no, absolutely not. Not in any way that makes sense given what we know about physics, biology, geology, and the conditions inside Earth. There's no habitable space down there. There's no liquid water ocean. There's no way for large animals to survive the pressure and temperature. There's no food source, there's no breathable atmosphere, there's no plausible mechanism for dinosaurs to have gotten down there in the first place. As science fiction, as imaginative speculation, as a premise for a story, absolutely yes. And it's a fantastic setup because it sounds plausible enough to people who don't know the details to feel deliciously, tantalizingly wrong. Science fiction has used hidden world premises forever. Hollow Earth theories, underground civilizations, lost worlds in isolated valleys. They're compelling because they suggest mystery and discovery and the possibility that Earth still has secrets. The water in the mantle transition zone research is real science, real discovery, genuinely interesting. But it gets distorted in popular retellings into something it's not. And that's fine for fiction. That's great for fiction, actually. Fiction should take scientific concepts and extrapolate them, play with them, ask what if. But let's be clear about the distinction between real science and science fiction. Which brings us to the purely fictional scenarios. Science fiction loves the idea that dinosaurs didn't just die and didn't just survive as birds, but that some lineages adapted, evolved intelligence, developed technology, built civilizations, and have been hiding from or coexisting with humanity in secret. This is a staple of science fiction going back decades. Doctor Who has played in this sandbox for literally decades, featuring reptilian humanoid species like the Silurians, later called Homo reptilia, and the Sea Devils, portrayed as ancient Earth species that predate humanity and that went into hibernation or underwater isolation and are now re-emerging. In the recent Doctor Who spin-off series, The War Between the Land and the Sea, an ancient ocean-dwelling species called Homo aqua emerges from the deep oceans, creating an international crisis and conflict with humanity. The premise explicitly plays with the idea of, what if dinosaurs survived and evolved and we're now meeting them again? Is that paleontology? No. Is it based on real science? Not really, beyond the very basic premise that intelligence can evolve in different lineages. Is it fun? Absolutely yes. Is it thematically perfect for extinction stories? Also yes, emphatically yes. Because it flips the entire narrative from they vanished forever to they waited. It transforms extinction into hibernation. It transforms loss into return. It creates dramatic tension from the collision of two intelligent species with competing claims to the same planet. That's good storytelling. That's using scientific concepts as inspiration for fiction while being clear that it's fiction. Option 2. The spaceship evacuation. This is my personal favorite ridiculous idea, my favorite absurd premise that I would absolutely watch as a movie or read as a novel, because it's so dramatically polite, so elegantly pragmatic. Picture it. Really visualize this scenario. The dinosaurs, or at least some dinosaurs, have been getting smarter over millions of years. Maybe there's a lineage of highly intelligent theropods, something like Troodon but further along, and they've developed tool use, language, scientific understanding. They see the asteroid coming. Maybe they have astronomy. Maybe they can calculate orbits. Maybe they understand what's about to happen even if they can't stop it. And they look at each other, look at the sky, look at the data, and they make a decision. Right, new plan. Staying here is untenable. The impact winter alone will be unsurvivable for any large organism. Our ecosystems are about to collapse. This planet is about to become temporarily uninhabitable. We're leaving. A secret space program hidden from the other dinosaurs because most species wouldn't understand or believe it. A reptilian ark built over decades or centuries, solar sails or generation ships or sleeper ships with cryogenic technology. A carefully selected population, genetic diversity, necessary skills, breeding pairs of critical species. They evacuate. They leave Earth orbit. They head for another star system, one with a potentially habitable planet identified through decades of astronomical observation. The non-intelligent dinosaurs, the ones who couldn't plan or build or leave, face the extinction. The intelligent ones, the evacuees, wave goodbye and disappear into the cosmic darkness. Good luck with the asteroid. We'll check back in a few million years to see if anything survived. Is it scientific? No, absolutely not. Not even remotely. Is it a wonderful way to end a script about mass extinction? Absolutely yes, because it lets you finish with the line, maybe they didn't all die. Maybe the smart ones, the planners, the engineers, just got better at project management than we ever gave them credit for. Maybe somewhere in the galaxy, there's a planet of dinosaurs, descendants of evacuees, telling stories about the old world they left behind. And maybe, just maybe, they look at their own sky sometimes and wonder if anything survived on Earth after they left. Pause. Let that image sink in. That's pure fiction. That's fun. That's playing with concepts. But it's important to label it as such, to be clear about what's real science and what's imaginative speculation. Science gives us real mysteries, real wonders, real stories more amazing than most fiction. We don't need to pretend fiction is real to make science interesting. We can enjoy both, keeping them distinct, appreciating each for what it is. Epilogue. Beat. Close. So, 10 ways dinosaurs died. We started with the asteroid, the big dramatic impact that everyone knows about. We went through heat, blast winds, tsunamis, earthquakes, acid rain, fire, darkness, volcanic stress, and the slow mathematics of population collapse. But the deeper story, the story beneath all of these mechanisms is this. Mass extinctions don't just remove life. They fundamentally rearrange what is possible. They reset the rules. They open new niches. They close others. They punish specialization and reward adaptability. They eliminate species that were perfectly adapted to the old world and create opportunities for species that can handle the new world. The KP extinction ended the age of dinosaurs, the Mesozoic era, and opened the age of mammals, the Cenozoic era. If the asteroid hadn't hit, if that particular rock had missed Earth by a few thousand kilometers, the world would look completely different today. Dinosaurs would likely still dominate. Mammals would probably still be small, mostly nocturnal creatures occupying marginal niches. Primates might never have evolved. Humans definitely wouldn't exist. Every mammal alive today, including you, including me, owes its existence to a cosmic accident, to a rock falling at exactly the right time to eliminate the competition and open ecological space. That's simultaneously humbling and empowering. Humbling because it reminds us that survival is often luck, being in the right place at the right time with the right traits. Empowering because it reminds us that after catastrophes, life persists. It adapts, it diversifies, it fills the empty spaces. Extinction is not the end of the story. It's a turning point. It's a transformation. And if you want to feel that transformation, that deep connection to this history in your everyday life, you can do it right now. Today, this afternoon, this evening, go outside, take a walk, look around, find a bird, any bird, a sparrow, a pigeon, a crow, a robin, a hawk, anything with feathers. Watch it for a moment. Watch how it moves, how it behaves, how it interacts with its environment. Look it in the eye if you can, if it lets you get that close. And remember, really internalize this fact. You are looking at the last living branch of Dinosauria. You are looking at a survivor, a descendant of the lineage that made it through the KPG extinction when so many others didn't. You are looking at living proof that catastrophes can be survived, that evolution continues, that life persists against impossible odds. That pigeon is not like a dinosaur. That pigeon is a dinosaur. Still here, still thriving, still successful after 66 million years, acting casual, unbothered, pecking at crumbs, pooping on cars, living its best post-apocalyptic life. The dinosaurs didn't all die, they just changed. They adapted, they became smaller, faster, more flexible, more diverse. They inherited the skies instead of the land. And if that's not the most hopeful message about survival and adaptation and the resilience of life, I don't know what is.